Hey there. Today we're going to be talking about, yes, the Doppler effect, also known as the Doppler shift, which I just demonstrated in that awkward moment. It is the Doppler effect. It is something that we can use and we see a lot of times with sound. So we're going to talk about with sound waves. It is the apparent change in an object's pitch of a moving object's pitch based on its position to an observer. That's a fancy term there. So let me kind of describe what that means. And that's what this video is going to be about, this effect of the Doppler effect. So first of all, recap real quick, something that's very, very important to understand when we're talking about this is it's a change in pitch, all right, based on the observer. So remember what we've talked about already, that pitch, right, is related to a sound wave's wavelength, all right, depending on its wavelength and its frequency, right, that's going to determine its pitch. If it has a very high frequency, it's a very high pitch. If it's a very low frequency, it's a very low pitch. All right. So let's see what does that mean for an object in motion here. So I have my little simulator, but it's actually something we've all experienced before. You know that sound I just did at the beginning of this, or if a car is passing you, you hear that siren. The moment it gets louder and louder and louder until right when it passes you, it almost seems to get like quieter. And it's not actually getting quieter. It's still the same sound. They're not turning up and down the volume of the ambulance. It's the change in pitch. It goes from a very high pitch when it's coming towards you and drops to a lower pitch. All right. So for example, here I have this car. Let's say this car is blaring on his horn. All right. And so we have you here sitting in the middle. That's you right there, sitting there, and you are experiencing that sound wave with 1,000 hertz frequency. So you're hearing it as a very constant, or a horn. All right. So far, that's what we have. Now, if we were to put this object in motion, something will change here. So let's set him up to go in motion. All right. Now watch the wavelength and thus the frequency. You can see the observed frequency change, and you can see the wavelength change as we put this car in motion. Notice what's happening to the waves in front of it. All right, so as the car is approaching me, all right, or you, we notice that the wavelength has gotten smaller in front, all right, and the frequency has gone up. We're now at 1,300 hertz. We know that based on that, that's a higher pitch sound. All right. It's actually, it's almost like the car is catching up with its own waves, bumping them up together. If we let it keep going, it's getting higher and higher. And then the moment it passes it, there's a sharp drop off in the frequency. Now we're at a frequency of about 800 hertz. We know that must be a much lower sound. So we went from the very high sound there as the pitch changed. All right, we didn't move. It was because the object wasn't moving, and it gave it a perceived change in pitch. It didn't actually change its pitch. It just seems like it did because it was catching on this side of it. It's catching up with its waves, and on this side, it's kind of running away from its waves. And so here we have we have an increased frequency. And here we have a decreased frequency, and we know how that affects pitch. All right, so we have a higher pitch over here, high pitch, and we have a lower pitch over here. This is what we call the Doppler effect. It's the apparent change in frequency due to an object in motion. All right, and now that can have different effects. So for example, let's make this object go. So these are sound waves traveling through air. Sound waves through air travel at about 343 meters per second. That's really fast. That's almost 600 miles an hour. All right, that's really fast. But what if I were to have the object go faster than its own sound waves? So I'm going to make this car go, let's say 40 meters per second. It's going to go faster than its own sound waves. All right. So when it goes, all right, it is actually going to be traveling faster. The people in the front are going to be ahead of its own sound waves. All right, it creates this pressure wave right here and right here. Creates this pressure wave, and it's breaking what we call the sound barrier. And that would actually create a sonic boom for the person standing here. That when that barrier crosses them, they would hear a big crack, big boom, or what we call the sonic boom. All right, because it is traveling faster than its own sound waves. And that's what we call going supersonic. Supersonic means literally going faster than sonic waves or sound waves. There's different levels. Going Mach 1 is going the speed of sound. Mach 2 is twice the speed of sound. Mach 3 is 3 times the speed of sound. The fastest jet we have so far is about, I think, like Mach 7.8, which was a jet that was specifically designed to see it has no other purpose except to go extremely fast, and it cost millions of dollars. And we just wanted to see how fast we could go. It was going 7.8 times faster than the speed of sound. Um, and so it's going to sound a lot different. Notice here, this person's hearing a frequency of only 400 frequency of 400 hertz. That's going to be a lot lower pitch. So it would hear the big crack and then a very low pitch immediately right after that because it's escaping its waves so quickly. All right, so that's my quick little tutorial of the Doppler effect. Hopefully that didn't take too long. It's the apparent change in object's frequency, thus pitch, because the object is in motion. All right. And so if you're not really sure, kind of look back over it again and make sure you copy down any notes that you needed to about what the Doppler effect is. Otherwise, thanks for watching and good luck, and may the science be with you.